In this video, I would like to do an example calculation of electric potential energy. And the situation I want to imagine is a model for a helium atom. And so what the helium atom is going to look like is, let me draw an axis here just to make things a little organized. We're going to have a nucleus which has a charge of plus 2 electrons worth. And then there are 2 electrons in this atom as well. Okay, so I'm going to have them be evenly spaced. So this one has a charge of minus E, and this one has a charge of minus E as well. Okay, and so we've got 3 charged particles here. I'm just going to label them 1, 2, and 3 to make the notation a little simpler. And I also need to pick a distance between these. So I'm going to just make up a distance, but a number you should sort of have in your mind for like what scale atoms are in terms of their sizes is that an atom is approximately 10 to the minus 10 meters in radius or diameter. This is just a ballpark, so they'll be within, say, a factor of 10 of that size typically. And so I'm just going to use that as the size here. So I'm going to say that this distance is 10 to the minus 10 meters, and similarly, this distance is also 10 to the minus 10 meters. That's a common enough unit, 10 to the minus 10 meters, that there's actually a name for that unit. So 10 to the minus 10 meters is sometimes called 1 angstrom, which is an A with a little circle over it. Okay, spelled like that. So that's named after a Swedish physicist, actually, Ångström. And so, that's a very common unit that's used. So you will very likely, almost certainly, see that at other points in your life. Okay, so what I want to do is find the electric potential energy in this case. All right, so to calculate that, the total electric potential energy is going to be the electric potential energy between each pair of particles. Okay, so I have to calculate the energy between 1 and 2, I have to calculate the energy between 1 and 3, and I need to calculate the energy between 2 and 3. All right, so if we had more particles, we would have lots and lots and lots of pairs. The number of pairs grows rapidly as you add more particles. Okay, so essentially what we want to do then is just plug in K, Q1, Q2 over R for each of these. So this one will be K, Q1, Q3 over R. And I should be specific about the R's now. So this first one was R12, the second one's R13, and the last one is K, Q2, Q3 over R23. So notice, because energy is a scalar, I can just add these together. I do not have to worry about components. I do not have to worry about anything else. I just make this equation where I add them all together. That's one of the things that's really nice about energies instead of forces. Even if they were not all in a line, that would still be true. Just add up the scalar quantities. Okay, so now let me plug in the values. So I've got K in this first one. Q1 is minus E, Q2 is 2E, and the distance is 10 to the minus 10 meters. And then in the second case, I have K, Q1 is minus E, Q3 is minus E, and then the distance is 2 times 10 to the minus 10 meters. And then in the third case, I have K, Q2 is 2E, Q3 is minus E, over 10 to the minus 10 meters. Okay, so I can see that I've got a lot of things that are the same in each of these. So I'm going to actually factor this before I plug stuff in. You could just plug in values this way if you wanted. So I've got a k e squared, and then the terms are going to be minus 2 over 10 to the minus 10 meters plus 1 over 2 times 10 to the minus 10 meters, and then minus 2 over 10 to the minus 10 meters. Okay, so if I add those up, then what I'm going to get inside is negative 2 plus a half minus 2. And so that's going to come out to minus 3.5 over 10 to the minus 10 meters. Okay, and then that is going to be that part. So when I write out everything, K is 8.99 times 10 to the 11 Newton meters squared per Coulomb squared. E is 1.6 times 10 to the negative 19 coulombs, which is squared. And then that last bit is negative 3.5 over 10 to the minus 10 meters. Okay, so some people were struggling in the gravitational cases where I asked you to work this out. So the way that I like to approach this is to do it in some steps. Okay, so I like to do the prefactors first. So that's going to be 8.99 times 1.6 times 1.6 times negative 3.5. Okay, and then I do the exponents. So I've got 10 to the 11 times 10 to the negative 19 times 10 to the minus 19 times 10 to the 10, because if I have 10 to the negative 10 in the bottom, when I bring it to the top, it'll be 10 to the positive 10. And then I do the units after that. So I've got coulombs will cancel because I have coulomb squared here and coulomb squared there. The meters will cancel because I have I have meter squared here, but I have only 1 meter here, so I'll have 1 meter left. And so then I'll be left with Newton meters. Okay, which is good because a Newton meter is a joule. So I wanted energy, and this gives me units of energy. Okay, so now I'm going to plug this into a calculator. So bear with me as I do this in real time. So my calculator has, okay, 8.99 times 1.6 times 1.6 times 3.5. Okay, so this gives me negative 80 for my prefactors. Okay, and then I do the times 10 to some power. So 11 minus 19 plus 10. I could probably do in my head, but I don't want to make a mistake. So 11 minus 19 plus 10 gives me times 10 to the negative 17 joules. Okay, so I'm going to make this into scientific notation, which means I have to have a number between 1 and 10 for that first part. So this is going to be negative 8 times 10 to the minus 16 joules. Okay, so that's it. That's the amount of energy that's in a helium atom. Does it make sense that it came out negative? Well, yes, because if I take one of those electrons and move it out to infinity, then that energy will go to 0 because I have taken those two objects infinitely far apart. And when I let that electron come back in, it's going to have a lower energy than that. Okay, so it makes sense that this came out negative. Now, how does this number compare to a real-life value, how much energy a helium atom actually has? Well, this is a bit of an overestimate. It turns out the true energy of a helium atom is in the neighborhood of 10 to the minus 17 joules. So this is, maybe 60 times bigger than that. But keep in mind, I just made up a distance, so that's part of the thing. And I'm also completely ignoring any kinetic energy. So in order for the electrons to stay in orbit, they have to be moving super, super fast. And that's going to contribute also to the energy. Okay, so this is how we go about calculating the electric potential energy in a case like this. If we had more particles, you would just calculate more and more pairs. And then if we had any other sort of thing going on, if we wanted to consider kinetic energy or what have you, then we would do the ordinary thing where we would take U initial plus K initial plus any other kinds of energy that are present equals U final plus K final, and then solve for the speed, solve for the distance, solve for whatever it is you're trying to solve for.